record this and share my screen. Okay, so functions.
So what is a function? A function is a system based on the relationship between the input and an output, in which every input has its own output. Oftentimes, a function is described as a machine, where an input is inserted into the machine, and based on that input, an output comes out. So defining a function. So any equation graphed on a coordinate plane with at least one variable. So each x value should have one y value, not two y values or any more than that, just one.
So now we're going to talk about function format and how a function is written. So it's often written like f and then x in the parentheses, which is read as f of x. And f can be replaced by any other variable. You can have g of x or any other letter. And after that part of the function is set up, the rest is just a regular equation. So that example would be f of x equals 2x plus 3. So now let's look at a function example. So we have the one from the last slide, f of x equals 2x plus 3. The input is x and the output is y. So as you can see, when we put in -1 as the x for the y, we solve and we get 1. Or when we put 0, we get 3 as the output, and so on. And these inputs and outputs create coordinates to graph the line of the function. So for the x value of -1, the y value of 1, you'd have the coordinate point -1, 1. Identifying functions. So in order to have a function, each input needs to have a separate output. And you can see that in the table again. And then here is another, not a function, because each input has the same exact output. So they all have an output of 3. So that would not be a function.
So when we graph a function, you can see that if one x value, as you can see this like line here, the vertical line, has more than one point on it or more than one y value, then it does not represent a function, because we know a function only has one y value for each x value. So basically this is called the vertical line test. So if you have a graph of a function, you can basically draw a vertical line, and if there are more than 1 point, so there only gets to be 1 at each place.
So that brings us to domain and range. So domain and range are two things you want to consider when looking at a function. So the domain is all the possible x values that work in a function. So for example, this example right here, this looks like a cubic root graph. So the domain of the example, it's -x is equal to or less than x is equal to or less than infinity. So this is basically just saying, because it doesn't have a specific endpoint, it's saying that x can equal all real values, all real numbers. So any real number between -infinity and +infinity, which is just every x value will work in this function. And range of this function, so this is all possible y values that work in a function. So all the possible y values that will work in a function. So in this example, the range of the example is 0 is less than y is less than 1. And we can tell that there is an asymptote at y equals 1 and y equals 0, because the function will not cross these asymptote lines. They will cross the line. They can go like really, really close to the line, but they'll never cross. So, it'll always be smaller than those numbers. So y will be, the y values for this entire function will be any value between, so we can assume that the graph will never pass 0 and 1.
So now let's go ahead and take a look at the different function families that exist and are commonly seen in different math problems, especially in higher math. So the top 8 that we have narrowed it down to are quadratic, square root, cubics, cube roots, simple rational, absolute value, exponential growth, and exponential decay. And we are giving you this code in order to make sure that you guys know for the following slides that show these different function families, what's the formula, what's the parent function, and what's the transformed function. So the first one we're going to look at is quadratic. So the basic quadratic equation will be a times b, the base, or times x to the power of b plus c. Now it's not obviously seen here because it was supposed to be in white, but as you can see, there is an exponent of to the power of, and you'll notice that we have the equation y equals x squared, which is the red line. And you'll notice that it creates this U shape. And then the transform function, you'll notice that there are different transform numbers that have been added or put in place for these different equations, and it will change the equation. So for example, subtracting 2 will make the equation move to the right 2, plus 18 will make the equation go up 18, and this half will make the equation more wider. Now, we have the next one, square root, which the equation is y equals a times x minus h to the power of 1/2 plus k. Square roots are often seen with different problems, so the exponent will always be to the power of 1/2. So, in this equation with the graph, y equals x to the power of 1/2 is our parent function, and you'll notice that it is this red line. And then if we apply different numbers to it, such as the half, multiplying the equation by half, subtracting the independent variable by 2, and then adding 18, you'll notice that the equation is shifted. And we have 2 other equations, cube roots and cubic. So our parent function is y equals x to the 3rd power, and you'll notice it's the red line. And then you'll notice how it's transformed with y equals 1/2 x minus 2 to the 3rd power plus 18 with the blue line. And with cubic roots, it's the same thing. There is a change in how the graph looks when you apply different variables to your equation.
So now we're going to look at the next 2 types of equations, simple rational equations and absolute value equations. So a simple rational equation is any equation with a variable in the denominator. So right here in red, we can see that there's a graph called a hyperbola. So this is a graph that has a vertical asymptote and a horizontal asymptote. So the form of the equation of this red graph is y equals 1/x. See how there is a variable in the denominator? Now keep in mind that this variable can be like anything. This denominator can be anything with the variable. Like it can just be x, it can be like 3x, it can be x like x plus 3x, it can be a binomial, polynomial, etc. So the reason there's a horizontal asymptote is that the value, like there's a vertical asymptote, because if you set as the x value, as the denominator gets bigger and bigger or smaller and smaller, as this value of the denominator gets closer to 0, the function blows up. Like if you have 1 over like 0.001, you'll have like a high value, like 1 over 0.001 is 100, and then over 0.0001,000 million, and etc. So as it gets closer to 0, the function blows up, and like as you get, like if it's negative, then it goes like downwards in the negative direction. And yeah, so that's why and if it's 0, then the function like completely blows up, it becomes undefined. So that's why the y value at x equals 0 is undefined. So yeah, anyways, this blue function right here represents 2 divided by x plus 2 and then plus 18. So the value outside the parentheses shifts it like upward or downward, and the value inside the parentheses, the 2, shifts it upward. So here we can see that the form of a simple rational equation is y equals 1 divided by a times x plus h plus k. So a, like, it increases the amplitude, I guess, of the function. I don't really know how to word it, but yeah. And then moving on, and then yeah, as you already know, like h moves it sideways, translation sideways, and k is translation upward or downward. And now we can move to absolute value. So here we can see the absolute value equations are shaped like V's. So you can see that the function never goes below 0. So the y value never goes below 0. So the function output is always positive, unless, like, of course, you change k or h. So here the red equation is a regular, apparent absolute value graph. So yeah, y equals absolute value of x, and that's denoted by these 2 lines. So the value will always be positive. Y will always be positive regardless of the sign of x. So here we can see that this blue graph, it's, I guess, a wider V, I guess you could say that. It's wider than the parent function, and that's because of this 1/2 on the outside. The 1/2 just tells you the, like, slope of each line, and then x plus 2 tells you x minus 2 tells you to translate it, like, sideways, and then plus 18 tells you to translate it upward. So yeah, you can't really, it's kind of like, because it's zoomed out, you can't really tell, but the function is actually moved 2 to the right. So this minus 2 tells you to move the entire function 2 units to the right, and then the 18 tells you to move it 18 units upward.
Okay, and then lastly, we're going to go over exponential growth and decay. So basically, the parent function for the first one is 2 power x, and then obviously, just like the ones before, the h and k values and then the a values at the beginning change it. So the changed equation, blue, is 18, it's like moved up by 18 and moved 2 to the right. And then for exponential decay, it's basically where it's getting smaller exponentially, not linearly. And you can see the equation there too.